Professor Belfrost's science class is back.
Okay, so welcome back. Professor Belfrost here, and today I will explain to you um, again physics. We will continue from the part that we left on the first lesson on physics, yeah, which is units and measurement. So if you're ready now, then let's start with this lesson today. So this is just the second part of physics, chapter 1, which is units and measurement. I will finish up this part, units and measurement. This chapter I will finish today. So for the next week, we will enter revision about units and measurement. So maybe this is a little long, but yeah. Okay, so I will review a little concept that I have explained to you in the first lesson. So measurement of any physical quantity is made in its own units by comparison with standard. Okay, so for a measurement to be made, it means that you need to apply a certain standard because yeah, though for example you are about to measure length, there are many standards that you can use. You can use meter, you can use feet, you can use you can use inch, you can use any kind of standard for using for the measurement of a certain physical quantity. So first is to determine which standard you will use. Then there are so many physical quantities, right? Fortunately, they are not all independent, so we can just pick up small numbers of physical quantity to be base quantities and just standards called base standards and divide all other physical quantities in terms of that. Okay, so in SI units, there are seven kind of physical quantity that be applied as the base quantity, namely the length, mass, time, electric current, temperature, amount of substance, and luminous intensity with symbol M stand for meter, kg stand for kilogram, S for second, A for ampere, K for Kelvin, and a mole for mole, and CD for candela. Okay, but mostly we will just deal with length, time, and mass. Okay, then all other units that are made by mathematically combining the fundamental or base units are called the derived units. There are many derived units, thousands, maybe hundreds or thousands of derived units because you can just make it by yourself if you want to express new physical quantities. But there are only seven base units. Okay, so that's the important for you. Okay, so there are two major systems of units that are used widely in this world. SI units, acronym for the French Les Systèmes Internationaux des Units, also known as the metric system, and the English unit imperial system. Nowadays, most of the country in this world has adopted the SI units for being used as measurement. And uh, what I know is that the country that still use English unit imperial system the most is US. Okay, so there are many metric prefixes that can be used to express a very large or small measurement. Yeah, there's on the slide. You can just take capture. I've also asked you to take the capture before, so I think you have done it. That's good for you. Okay, so we can also use scientific notation to write down that measurement using the format x times 10 to the y, which y is said to be the order of magnitude. So for example, 800 and 450 both can be expressed by 8.0 times 10 to the 2 and 4.5 times to the 2 have the same order of magnitude, which is 2, yeah, because the exponent of 10 is 2, right? Okay, here, please note that I write 8.0 and 4.5. It means that I use two significant figures. But you can only know this, how many significant figures to be used when we have the measurement, right? Because we can know how accurate we can show the measurement. Okay, I will also re-explain about significant figures in this lesson. Okay. We can do unit conversion by first determining the conversion factor. So conversion factor is just actually a factor for converting one uh, one amount, not one amount, one physical quantity to another physical quantity that actually uh, express measure the same thing but in different amount. For example, if I say 60 seconds, it equals 1 minute, right? They both used to measure time, so this is consistent dimensionally, uh, though they have different amounts, but because they are just the result of we using the different standards, so it makes sense. So there's the conversion factor being applied, and the method we use is called the chain link conversion. Okay, that's the review. Enough. We go through the discussion today. So there are two quantities in physics. Yeah, first is scalar and the second is vector quantity. A scalar quantity has magnitude only. For example, we have mass, volume, energy. But a vector quantity has magnitude and direction. For example, force, velocity, acceleration. For example, there are still many. Yeah? When two scalars are added together, the total is just simply a arithmetic total. But when we take two factors to be added together, then their direction must be taken into account. A triangle of factors may be useful. But I will not discuss the scalar and vector quantity furthermore because this will be the topic, the subtopic of the next chapter. Okay. First focus of today's video is to discuss the measurement of length using vernier calipers and micrometer screw gauge. Okay, so yeah, there are many device for measuring, for doing measurement, and there are length, mm, mass, time, yeah, which is the base unit. But uh, I have more interest to explain for you the measurement of length because there are many books that covering this. Yeah, but I will not go for measurement of length using just rule because you can just use your rule to do the measurement. You have no other way. But for vernier caliper and micrometer screw gauge, maybe it is not a very general thing. Okay, so when rule can measure to the nearest millimeter, a vernier calipers can measure to the nearest tenth of a millimeter. Okay, so to read the measurement using a vernier caliper, then first read the millimeter from the main scale marking before the zero on the vernier. Okay, you see the main scale marking before the zero on the vernier. I want you to pay attention to the sentence. Okay, and then B, take the next figure, tenths of a millimeter or a centimeter from the first vernier mark to coincide with a main scale mark. So I want you to pay attention. Uh, in most books that I use, that the vernier measurement is described in millimeters, but for some books that I also use, there are centimeters. So what I want you is to pay attention to the units they use in the vernier. You see, like in this picture, there's written millimeter. It means that the measurement is made in millimeter. But for some vernier caliper, they use centimeter. Okay, so you can see in the picture, it's not millimeter written, but centimeter. We just apply the same rule. I mean, there's the same way to do the measurement, but the unit is just different. Yeah. But in all my videos, I will just make it uniform. I will use millimeter. Okay. So let's work on the first example using the picture that I've provided you in the slide. Okay. So from the picture above, the main scale reading is 11 millimeter. Just before the zero on the vernier scale, there is 11, right? While the value reading is, you see, one that coincide. Okay, uh, one no, two no, three, four. Okay, four coincide with the main scale of 15, right? So 10 times 4, which is 0.5 millimeter. So the final reading of measurement is 11.4 millimeters, right? A vernier scale can be used to measure to the nearest tenth of a millimeter, while a micrometer screw can measure to the nearest hundredth of a millimeter. Okay, so a micrometer has an accurately turned screw thread. When the thimble is turned through one revolution, the jaws are opened or closed by a predetermined amount. With most micrometers that is used widely, this amount is 0.5 millimeter. So because there are 50 divisions on the thimble, so turning it through one division closes or opens the jaw by 0.5 divided by 50, which is 0.01 millimeter, yeah, hundredths of millimeter. To do a measurement using micrometer, first take the reading of the micrometer of the millimeters and half millimeter from the barrel. Yeah, this is the same as the main scale in vernier. Okay, and then B, take the reading from the thimble. This is the same as the vernier scale in vernier calipers. C, add the reading together. So you are ready now. Then let's work on this. So from the picture, we can see that the reading on the barrel is it is 1, 2, 3 liter, 3.5, right? 3.5 because we have this short marking there, okay? So 3 plus 0.5, 3.5 millimeter. While the reading on the thimble is, see, 21, 22, the 22 on the thimble. So we have 0.01 times 22, which is 0.22 millimeters. By adding it together, then we find the final reading, which is 3.72 millimeters. Okay, so that is about measuring the length with using the vernier calipers and the micrometer screw gauge. Okay, now we enter some terminologies used in measurement. Okay, science is based on experimentation that requires good measurement. Okay, the validity of a measurement can be described in terms of its accuracy and precision. Accuracy is how close to the real value a measurement is, while precision is just part of accuracy that the experimenter controls by the choice of measuring instrument and the skill with which is used. Okay, or how well repeated measurements of something generate the same or similar results, or how close together the measurements are when you measure the same thing several times. So actually, um, a precision is just another term of repeatability. Okay, so to understand the concept of accuracy and precision, I will choose to show you the picture. Okay, you see. So here's the picture. For example, so that this is a GPS location detection. So I want to find. Okay, so the circle on the center is the exact location, the location that we want, and the uh, black dots is the location shown or location detected by the GPS. Okay, so there are 1, 2, 3, 4, 5, 6, 7 measurements that we make to determine certain place uh, on the map using GPS. Let's see the left top picture. Okay, the top left picture. The first picture shows us that the measurement, I mean the detection of the place, is kind of random, yeah, and most of the dust not near to the center, so it has very low accuracy and low precision. How about the picture next to it on the right, top right? Okay, so we see that the measurement is not random. It uh, is, yeah, they all being grouped in a certain position near to the uh, top left, but we see that this is not the right place that we actually want. So it has low accuracy but high precision. How about the third? The third is, yeah, you see that they are all near to the center or the expected result, but they are a little dispersed. So it has high accuracy but middle precision or low precision. And what we want is the fourth picture, the bottom right one. Okay, it has high accuracy because you see that all of them uh, are near to the exact result that we want, and they are all not very dispersed. They have high precision or they are repeatable. The measurement result is repeatable. Okay, so accuracy and precision of measuring system determine the uncertainty of a measurement. It is a way to describe how much measurement deviation from the actual value. Okay, so the uncertainty in a measurement, often denoted as A, okay, a measurement. I mean the result of measurement is denoted as A. Okay, is often denoted. The uncertainty is often denoted as delta A. Delta in small letter. Okay, this is the absolute uncertainty. There are many factors that contribute to this uncertainty. First, the limitation of the measurement device. B, the skill of the person making the measurement. C, the irregularity in the object we measure, and the other factors that affect the outcome. Most of the time, uncertainty is expressed in terms of percentage uncertainty, yeah, which is percentage uncertainty equals delta A over A times 100%. Why I say that the percentage uncertainty gives us a more clear picture of how accurate or inaccurate measurement of are being made, because here, take an example. For example, we are measuring the length of a we are measuring the length of a road, or we and the second measurement is we are measuring the length of a paper. Yeah, for the measurement of the length of a road, we miss it by 1 kilometer. Okay, 1 kilometer. But for measurement of the length of paper, we miss 1 centimeter. Certainly 1 kilometer will make more than 1 centimeter miss, but because we use different we use different standard for measuring the length, then it doesn't make sense to compare between 1 centimeter and 1 kilometer case. That's where percentage of uncertainty has its use. Okay, so go to the example. A result recorded as 84.5 seconds, and the reading we see is reported as 84 plus 5 plus minus 0.2 seconds. Then the 0.2 seconds is the absolute uncertainty, while the 0.2 over 84.5 times 100% equals 0.24% is just the percentage uncertainty. Okay, so there's always an uncertainty anything we calculate from measuring quantities. An important factor in the accuracy and precision of measurement is the precision of the measuring tool. Okay, we always expect that the tool that we use to measure values have a very small increment in the scale. Okay, to create a more precise measurement. The number of significant figures in a measurement indicates the precision of the measuring tool. It is also called the resolution actually. So here is a review on zero. I'm not explaining again. I want you to take capture of it because I missed to provide you a slide on the last lesson, but I inserted in this lesson. Okay, and here is just another review on significant figures for various numbers. Okay, I also forget to bring the slide on the last lesson. And here I want you to review it by yourself because actually the concepts be given on the last lesson. Okay. So when dealing with measurement with different degrees of accuracy and precision, the number of significant digits in the final answer can be no greater than the number of significant digits in the least measured value. For multiplication and division, the answer should have the same number of significant figures as the starting value with fewer significant figures. For example, we are about to find area of a circle with radius 2.0 meter. Okay, so here is expressed in two significant figures, right? So A equals pi times r squared, which is just pi value times 2.0 meter being squared. And we have actually a very long, if we calculate using calculator, we have some blah 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 blah. But we just need to take two significant figures by rounding off to the nearest decimal place. Okay, so we have the result with us 4.5 meters squared. Well, for addition and subtraction, the answer should have the same number of places as the least precise starting value. For example, we bought 7.56 kilogram of potatoes measured using a 0.01 kilogram precision scale, and then we drop off 6.052 kilograms measured using the 0.001 kilogram precision scale, and then finally we added 13.7 kilogram more potatoes that we measure using scale of precision 0.1 kilogram. Then in total we have, you see, 7.56 minus 6.052 plus 13.7. While we calculating using calculators, we have three decimal. We have to 3 point decimal, right? I mean, we have uh, tenths, we have hundreds, and we have thousands place. But because we only limited to express it to the least precise starting, I mean, we are we have to express it to the least precise starting value. Which is the least precise starting value? That is 13.7. So we just use, I mean, one decimal place, 0.1 decimal place here, okay? So we express it as 15.2 kilograms. Okay, you can round off. Yeah, rounding off rule, I will not explain it again. Okay. An error is a mistake in taking a reading. Yeah. This can be reduced by taking more care or ensuring instruments are correctly calibrated before their use. Okay. By repeating a readings, we have chance to reduce serious error. And there are two categories of error. First is random errors and second is systematic error. Random errors occur due to lack of precision in taking readings, slight changes in experimental conditions and making value adjustments when taking measurements, and this error led to values differing from the true value by random amounts every time we take the measurement. Okay? While systematic errors generally occur because of faults in a measuring instrument or are repeated errors such as parallax error, which we are not looking perpendicularly at a measuring instrument. Okay? The most common mistake is zero error. Zero is not lined up correctly from the first start when we are going to measure something. Okay? Systematic error led to values differing from true value by the same amount or by the same fraction each time we do some measurement. Last but not least, lesson in this chapter is dimensional analysis. The dimension of any physical quantity expressed it depends on the base quantities as a product of symbols or powers of symbols representing the base quantities. So because we have seven base quantities, we also have seven symbols for the dimensions, right? Length L, mass M, time T, carbon I, temperature theta, amount of substance N, luminous intensity is J, all in capital letters. Okay. So pure numbers are dimensionless quantities, sometimes called of dimension 1, which have all 0 for the 7 powers. Physicists often use square brackets around the symbol for a physical quantity represent the dimension of that quantity. For example, if r is radius of a circle and h is height of a power, then r bracket equals h bracket equals L capital. Okay. Okay. So we do some check. Okay, I want to ensure that you understand the concept. Okay, for example, we know that the formula for obtaining density rho equals mv, yeah? And we know the dimension of m is just m capital and v is just L capital cube. Okay, then the dimension of rho is m capital divided by L cube L capital cube, right? So m times L to the minus 3. That's very simple, right? Any mathematical equation relating to physical quantities must be dimensionally consistent. Okay? Meaning the equation must obey the following rules. Okay, first, every term in expression must have the same dimension. Second, the arguments of any of the standard mathematical functions such as trigonometric, logarithm, exponential functions that appear in the equation must always be dimensionless. Okay. So that's the lesson for chapter 1. We have reached the end and now we practice a little, right? Okay, so first, given the measurement down using the Fernand caliper is shown as following. Determine the reading. Okay, so we see the main scale is 1.123. Okay, so the main scale reading is 1.3 millimeters. You see the position A. Okay, And then the failure reading. The failure reading is, yeah, it has been shown because it's very hard to see this small picture. It has been shown the one that I mean the same line is in the B position, which is 6 for the Fahrenheit scale. So 6 times 0.01, that is 0.06 millimeters. So the final reading is 1.3 plus 0.06, which is 1.36 millimeters. Now we are doing measurement using micrometer screw. So determine the reading. Okay, so for the shaft, yeah, the for the shaft, we have for the barrel, we have 2.5 millimeters, right? While for the drum of the thimble, we have 30, 31, 32, 33. 33 times 0.01, which is 0.33 millimeters. So the final reading is 2.5 plus 0.33 millimeters, which is 2.83 millimeters. Okay, third question. We are interested to know how much $1 trillion actually is. Say that we were given that amount of money in $100 bill. If we made 100 bill stacks and use them to cover a football field between the engines and using feet or inches rather than meters because football fields are measured in yards, make an approximation of how high the pile would become. One of my students said 3 inches, other 10 feet. How about you? Which one is true? Let's check. Okay, so information. A single bill are approximately 3 inches by 6 inch, while a stack of 100 of the bills is about 0.5 inch thick. Area of a football field is 100 yards times 50 yards if you don't know. Okay, so the answer, let's go to the solution. First, let's calculate the value of a stack of 100 bills. So length times width times height, that's the volume of the stacks, right? So 6 times 3 times 0.5. So we have 9 inches cubed with us. Next, calculate the number of stacks. Know that $1 trillion equals to 1 times 10 to the 12 dollar. I know that maybe in British system this is not called a trillion, right? Okay, and a stack of 100 of uh, $100 bill is equal to $10,000 or 1 times 10 to the $4. So the number of stacks we will have is 1 times 10 to the 8 stacks. While the area of football field is 100 yards times 50 yards, yeah, this expressed in yards, and we need to convert this quantity to inch because all other measurements in inch. Okay, so the 5,000 yards square, we convert it to inch. Okay, very easy. So we just need the chain link conversion rule, and we have the area approximately 6 times 10 to the 6 inch square. Okay, then we need to find the volume of all the 100 bill stack. Okay, so 9 inch cube per stack, yeah, one stack times 10 to the 8 stack. So we have 9 times 10 to the 8 inch cube. How about to determine the height? To determine the height, we just need to use this equation. Volume divided by area. 9 times 10 to the 8 divided by 6 times 10 to the 6. So we have 1.5 times 10 to the 2. Maybe you ask, why do you have to convert it to 2 times 10 to the 2 inch? Yeah, approximation. We have a good number for us, 1.5. Why convert it to 2 times 10 to the 2 inch? Because we have used one significant figures for all of the measurement starting from the first time we solving this problem. So we have to be consistent. So we round this to be 2 times 10 to the 2 inch to stick with the one significant figure rules that we have decided from the first time. Okay, so it equals to 200 inch. Now we convert it back to feet, and we have about 7 feet. Okay. Number 4. Determine the diameter of the ball bearing being measured. Okay, actually this question I made it's not because I'm silly. I'm keep repeating the same thing because in this, I want you to pay attention to the error being made. Okay, so the reading on the barrel on the left picture is actually 3 millimeters, while the reading on the thimble is 0.17 millimeters. So in total 3.17 millimeters. But you know that in the right picture, it's shown the initial position of the measurement before the measurement being made. Okay, so there's a zero error here in the initial reading. It is off by minus 2 times 0.01 equals minus 0.02 millimeters. So the true diameters, we need to subtract this amount. Okay, so 3.17 minus negative 0.02, that equals 3.19 millimeters. Okay, and the fifth, the last question. Consider the physical quantity S, V, A, and T with dimension. S is L, V is LT to the minus 1, A is LT to the minus 2, and T is T. Determine whether each of the following equation is dimensionally consistent: A, B, and C. Okay, so for A and B, there are no trigonometric, logarithmic, and exponential function in the equation. So we need only to look at the dimension of each term appearing in the equation. So phi is Lt to the minus 1, T is T, A is Lt to the minus 2, T is T, right? Okay. How about the constant? We don't pay attention to constant because it doesn't have any dimension, right? So don't obey. We only need to check the equality of the dimensions. So we arrange the equation as shown in the slide, and we do some uh, calculation, manipulation, and we have the last form, L equals L plus L. I'm not saying that L equals to L, right? We are not doing calculation here. We just want to compare if the dimensions, if all have the same dimension. Because all the terms have the same dimension, then this equation is dimensionally consistent. Okay? B, the same as before. But after we doing the cross-check, none of these three terms have the same dimension as any other. So this is not dimensionally consistent. Or this equation is nonsense. Okay, how about the third one? It involves a trigonometric function, so we need to first check the argument inside the trigonometric function, if it is dimensionless or not. Okay, so at squared over s, so a is lt to the minus 2, t is t, s is l. We do it 1. Oh, so the argument is dimensional. Good to go. Now let's check the dimension of the left and right expression, if they agree with each other or not. So we have the dimension of phi is L to the minus 1, while uh, any function is just 1, right? The value. So Lt to the minus 1 is not the same as as no dimension. So oops, the two terms have different dimension. I'm sorry, the equation is not dimensionally consistent. Okay, so I've done with my uh, with giving you some review and practice. Now I want you to practice by yourself doing exercise. Please take a screenshot. This is the first question. This is the second, third, fourth, and fifth, and sixth question. I want you to solve first. Okay, pause this video, solve it first before checking your answer to the solution, the answer. Okay, so that's being said. Thank you for watching, and here is information for you today as usual. Okay, so Winston Churchill once said, "Success is not final, failure is not fatal. It is the courage to continue that counts." Okay, so even if you fail in your subject, don't worry, you still have many times to, yeah, to have a new start. Okay, just chill out and always be happy. What you need is just courage to continue your way. Yeah, because courage is what with that will what values in your life. Okay. So thanks for watching. Here's your to-do list. Subscribe to my channel. Give a like, comment about your thought, and share this video to your friend. Okay, that be my class, as you have known, will be on every Tuesday, Thursday, and Saturday, except if I have some prior announcement that I cannot give a lesson on that day. Okay, and keep watching. Be thoughtful. See you. Goodbye.